In the previous segments, I explained the basic principles and theory behind pre-stressed concrete. Now let's take a look at the types of structures that benefit from this type of active reinforcing. We'll start on the ground with house foundations. In the United States, for several decades, we've used post-tensioned pre-stressing steel installed in a flat profile in the middle of the concrete slab to squeeze that slab together and increase its bending strength, like I discussed earlier. We do this here because in some regions where the soil that the slab sits on contains a lot of clay, the ground swells and shrinks as it gets wet and then dries. This swelling and shrinking puts a lot of force on the slab, and it can cause it to bend and break, which is obviously not something we want since this slab is the foundation that's holding up our house. Under these conditions, post-tensioned pre-stressing can be a very economical solution to creating a slab that's stiff enough to resist that bending. While we're on the ground, let's look at some bigger slabs. Remember that I already talked about how these slabs are going to shrink and crack, and I discussed a very common method of dealing with this by placing control joints to force the concrete to crack in a controlled and predictable manner inside those joints. But sometimes those joints are not a desirable feature in a concrete slab. Think about tennis courts. I would rather not have a bunch of joints that could become tripping hazards. Or look at large warehouse floors where I might be using heavy forklifts day in and day out. Every joint becomes a potential maintenance problem as the hard wheels of the forklift hit them constantly throughout the day. In these cases, the designer may use a design that employs the squeezing benefits that we've discussed to squeeze the slab enough that cracks don't develop as the concrete shrinks, or at least they get squeezed together and closed up as the shrinkage is occurring. I've constructed hundreds of tennis courts this way. In fact, I got to go back to my old high school where the school district was reconstructing all of the tennis courts, something like 9 or 10 concrete slabs, and they're big. They're 60 feet by 120 feet. They were originally designed as 6-inch thick slabs with a bunch of rebar. And I was able to propose a redesign to a 5-inch thick slab with just post-tensioned pre-stressing steel. The pre-stressing steel, combined with some techniques to reduce the friction between the slab and the ground as it shrinks, and some good timing, resulted in huge cost savings, and we have these big concrete slabs out there with no joints or cracks to trip over. Let's move up into the air. Up in the air, we can use the advantages of pre-stressing to get concrete to span long distances, helping everything from bridges to buildings to parking structures. Obviously, bridges need to span over something, so we can use all the benefits that we've discussed of active reinforcing to build that bridge out of concrete while getting it to span much further than we could with just passive rebar reinforcing. And I can do this with precast, pre-tensioned concrete that's fabricated at a plant and pieces are hauled out to the job to be erected, or I can use the cast-in-place post-tension method of construction to get the same benefits. Same thing goes with parking structures. I don't want a lot of columns that I have to drive around in a parking structure, so I use pre-stressing to span longer distances between those columns so I can push those spans out to 60 feet or more. And again, I do this with either precast pieces or using the cast-in-place method. Buildings are another case. In many types of buildings, an architect would generally prefer to have as much open space to work with as possible inside without a bunch of columns getting in the way. So again, I can use pre-stressing to get concrete to span over greater distances. But I can also use it to decrease the thickness of the floor plate or make the concrete section thinner because I have a stronger piece of concrete. Sometimes this can provide a real benefit from both an economical standpoint and even a feasibility standpoint. Take something like a 10-story building. If I used structural steel beams to build this and span the distances that I need to span, I could end up with a floor plate or a section of that beam in the floor that's 18 inches thick at each and every floor. But I might be able to get the same spans with an 8-inch thick cast-in-place post-tension concrete section. Think about it. If I save 10 inches at every floor in that 10-story building, I knock 100 inches off the height of that building. That translates into a lot less external cladding material since my building's shorter. In some areas, that height itself, though, might be an issue. Think about buildings next to airports. They're going to have height restrictions. So reducing the overall height of a building might be a really big issue. Or it might allow the designer to actually squeeze in one more floor and still come in under those height restrictions. These are some great examples of how we use pre-stressing to increase the usability of concrete. But when we start actively reinforcing the concrete, squeezing it together and adding the uplift that I've discussed, it does get a little technical. So let's go to the next video and look at a few things you need to be aware of.